Welcome back YouTube. Today I'm showing you how you can use differential equations to analyze circuits such as the high-pass filter I'm going to be showing you. So imagine that we have a voltage coming in and we will just call this voltage V, and it's going to be any old function of time. So it can vary over time. You can think of it as an AC voltage, or it can be an AC with a DC offset or whatever. And that's going to be on this wire, and first it's going to go into a capacitor with capacitance C, and then it's going to go through a resistor with resistance R, and then it's going to go to ground. So in my last video I showed that capacitance is expressed as charge over voltage. If we rewrite this a bit, we see that the voltage over the capacitor is going to be the charge divided by the capacitance. And of course from Ohm's law we know that the voltage over the resistor is going to be current times the resistance. Current is moving charges, so we can rewrite this as the derivative of charge with respect to time multiplied by the resistance. And sometimes in physics we use dot notation, which means we put a little dot on the Q, and the dot means we take the time derivative. Now from, I think, Kirchhoff's law or something, we know that the voltage from this point, which is our ground reference, which is per definition zero voltage, to this point is the sum over this voltage and this voltage. So we know that V, this V, is going to be equal to Vc plus Vr. So this will be Q divided by C plus Q dot R. And what we have here is what's called a differential equation. We have some function for the charge Q. We don't know what the function Q is, but we know that it has some relation with its own derivative. So I'm going to rearrange this equation a bit. It's standard to put the derivative on its own on the left side. So we're going to write Q, derivative with respect to time, equals V over R, where V is our input voltage, can be any function of time. We subtract, because we move this to the other side, Q divided by CR. Oh, there goes my chalk. Let me be a little bit more clear. C and R are just constants. They are determined by our circuit, but the charge Q is a function of time, and its derivative is also, and our input voltage was also a function of time. This thing here is what's called a linear ordinary differential equation, and to solve it we first have to pretend that this part doesn't exist. That's called the homogeneous case of the ODE, and I'm going to simplify a bit. I'm going to say Q, the time derivative, is equal to negative A, where A is 1 over CR, times Q. If you know anything about functions, there can only be really one type of function, family of functions, that has its derivative be a multiple of itself, and that is e to the power minus a, and a was 1 over CR times t. And this is one solution, but of course you can also multiply this by a constant. I'm going to call this constant Q0 for initial charge. And so what we've done, we've just removed the input voltage. We say there's no voltage on here, and then we find that if we have some initial charge, Q0, and we let time run, then this charge is going to exponentially decay. This is what this equation says. And it is a result from our differential equation over here. And the rate of decay is proportional to the inverse of the product of the resistance and the capacitance. So the bigger your capacitance or resistor, the slower the decay is going to be. Which makes sense, because if you have a big capacitor, there's a lot of charge. And if you have a big resistor, the charge can't escape very quickly. Now that we know Q, we can also easily calculate Q dot, which is not the charge on the capacitor, but the current through our system, and we can use Ohm's law again to calculate the voltage at the point in between the capacitor and the resistor. Because we want to know what the voltage compared to ground, and compared to ground, that is just going to be I times R, and I is the same as Q dot. So we can differentiate this with respect to time, and we find that VR is going to be minus Q naught over CR e to the power minus 1 over CR t, and then we also have to multiply by R. So let me put this R here, and this R is going to cancel here. So in the case where we have some initial charge on this capacitor and we're not feeding it any voltage, this is going to be the voltage over our resistor. It's not so interesting, but we're going to use this homogeneous case to solve the more general case. So let me make some room and we can solve the general case. So this is the differential equation that we found for this circuit. We solved the homogeneous case if our Vt is 0. The method I'm going to use to solve the general case is called variation of constants. Differential equations are quite difficult to solve. A lot of it is trial and error. Of course, mathematicians have constructed all sorts of tools to solve them, and the method I'm showing you is kind of a historical use case. A modern mathematician would just say, oh, I know the solution, it is a linear equation like so and so, and there's maybe a more elegant way to show this proof. A variation of constants feels very trial and error, and like how am I supposed to come up with this? I will put a more mathematically rigorous proof for this sort of ODE on the screen if you're interested. So earlier I said that our solution was going to be Q of t is going to be some constant, and now I'm going to call it f, multiplied by e minus 1 over CR times t. This was the homogeneous solution, but now we want to know our solution for V. And the idea is that we're going to simplify our equation by varying our constant, meaning this f. And last time, by the way, this f was the initial charge. But now I'm going to make it a function of time itself. So we're going to assume this f is a function of time, and then we can calculate what our time derivative of q is going to be. That would of course be the time derivative of f multiplied by e to the minus 1 over CRT. And this is just using the chain rule. We're going to subtract of course, because we're going to get this minus 1 over CR term from this f again, e of minus 1 over CRT. Now something useful pops up, namely this is exactly Q. If we remove this and fill in Q, then we notice that this is going to cancel a lot of things in our initial equation, because this term is just exactly this term. And if we plug this, what we call an Ansatz, so this is called an Ansatz from German. I don't know the English word. In Dutch it's Annahme. I think guess is the best translation. If we have this guess, then we find that our equation is going to simplify to ft e to the minus 1 over CR t, and this is the time derivative of f, has to be equal to this part, right? Because this is that, and then this has to be that. So that's going to be v of t divided by r. And now we can simply solve for f. Take this term to the other side. Of course, if you divide by a power, the minus becomes a plus. So we find that f, the time derivative of f, is going to be, I'm taking the r in front, and then v of t multiplied by e to the power 1 over CRT. And then we know what the derivative of f is going to be, but of course we want f itself, and for that we just have to integrate, and the r you don't have to integrate over the r because it's constant. We're integrating from 0 to t, and we replace t with an integration variable. I'm going to call it s ds. And that's our solution for f. And if we know f, then we can calculate q. Of course, we also have to add a constant to think about what the constant is. We have to think about what q of 0 is going to be. So if we plug in t as 0, this is going to be 1, because e to the power 0 is 1. And then we want this to be q0. So this is also going to be 0 because an empty integral is 1, so this is just going to be q of 0. And that was our constant from the last time. Now we can assume that our capacitor is empty at the start of our problem to simplify the mathematics. So I'm going to say q of 0 is 0. Of course, now we found a solution for the charge. And then we can calculate the current, and from the current we can calculate the voltage at this point. And to continue the discussion about this voltage, I am going to go to the computer and show you on decimals. Hello, it's computer Ari here. Here I have the equation that I got before. This is the charge on the capacitor, and I'm not plotting it, but you can see it there. I also calculated the output voltage, which I called O. That's the blue line. And then the red line is the input voltage. You see that if we have just a constant voltage, our output voltage has this exponential decay. If we add an AC component, that is going to go through after the DC component has decayed. So this is why capacitors work as AC couplers. Here I have this initial charge that I had in my equation. I'm using a small letter q instead of capital. If I change that, you can see that also changes the voltage across it, but there wouldn't be any reason in a normal circuit for your capacitor to have an initial charge. So let me just keep that on 0. And if we decrease the capacitive value, we see that the initial voltage goes down a lot quicker, but we also get a lot less AC voltage across it. But if we increase the frequency, then we see that the amplitude of the output voltage goes up again. So that's why it's called a high pass filter. Now I could do a video where I actually plug in some voltage here and explicitly calculate this integral. And then if you plug in something like the cosine of Wx, yeah, this is not the frequency, this is the angular frequency. So usually we call it omega or W. If you plug something like this in for your voltage here, then you can explicitly calculate a solution for this integral. I'll leave that up as homework, and I'll give you a little tip. It's a lot easier to not use the cosine, but to use e to the power I omega t or x, which is basically the same thing as a cosine, only it has a complex component. Or you can use Euler's formula for the cosine if you want to have it be a cosine, and then this integral is going to be a lot easier to calculate. And you can just go back to the real component if you want to know the actual voltage. So leave a comment if you want to see that video. And in that video I could also look into the Fourier transform of this thing, and then we can discuss how good of a low pass filter this thing actually is. So that was the video. See you next time. Bye.